Welcome back to the third video about the details of the Allegro A1335 precision Hall effect angle sensor. In the first two videos we covered all of its primary registers, and that enabled us to properly initialize it, to read out, of course, an angle, but also to read the internal chip temperature as well as the magnetic field strength. Cards here, links in the description. Now it's high time to have a look at the extended registers, which are not registers at all, as we will see. Enjoy! I've already shown you that graphic here in the very first video, but I pretty much skipped over it because it's actually missing a register here. Anyways, in the first two videos we covered the primary registers starting from control and ending with extended error masks. Now we will use the first 6 primary registers to actually access the additional registers on the extended addresses. Please note that through accessing these extended addresses you cannot only read and write to the SRAM and the EEPROM, but also initiate the execution of commands which might return data. The list of extended addresses starts in the programming reference at page 36 and continues on until page 40 for 5 whole pages. And we will not have a look at each and every one of these addresses. The list makes a distinction between reading from addresses and writing to addresses. So, for example, these first 2 lines here are both the SRAM addresses, which are realistically, my red correction here, going from 0 to 1A, and you can both read and write these addresses. The next column here gives you some idea if you can access the addresses. Most of the time it's simply a yes, but sometimes something like yes unless LM equals 1 is stated. So LM is a flag somewhere in the EEPROM, I think. I'm not quite sure, and it's the log memory flag. So you can lock the SRAM as well as the EEPROM. That's the log EEPROM flag here, LE flag, against writing. Some of the extended addresses are not accessible while the CPU is in run mode. For example, here, writing to the EEPROM is only possible if you put the CPU of the chip into idle mode. Finally, writing a keycode to a specific keycode extended address is required if you want to write to certain of the extended addresses. By the way, the keycode is really just a fixed 32-bit number. I already mentioned in this series that this is an automotive grade chip, and so a lot of fail-safes are built in. So, the first 2 lines here were about reading and writing the SRAM. The next 2 lines here are the extended addresses for reading and writing the EEPROM, the extended addresses 0306 to 0319. Also here, read my corrections. There are other addresses mentioned here, but they are undocumented, so why would you read or write them? Anyway, we will not write the EEPROM in this video series because that would require sending 2 very well defined, in timing and rising edges, 17-volt pulses on the VCC line. Automotive again. Anyways, the next 2 address ranges here are for reading the EEPROM with margining, with 0-volt margining and 4-volt margining. Without going into the details, you can use that to verify the quality of your EEPROM writes to each and every cell, or 32-bit word in the EEPROM. And then, starting with FFZ0, come all the command addresses. And these continue until page 40, of course with some gaps here in the extended addresses. There are not 200 commands, but there are a whole lot of commands. Anyway, the very last command here, FFFF, returns the ROM version of the chip, and that should always be 133500BA. And we will be using that command later on to verify if our read extended address code is really working. Let's have a short look at the SRAM and the EEPROM addresses too, which were only summarily mentioned in that first table. In the SRAM, you first find a block of registers here that enable you to set extended configuration options. Yeah, for example, setting a 0 offset or angle limits. They second give you more information about what's going on in the chip. So we have here a command status and a filter error. And third, you can configure a filter here with several factors for averaging, not really averaging, it's a complicated algorithm, but setting up a filter to filter over several samples. The second block of registers, and that continues down to 1A, so 15 registers in total, allows you to set up a linearization for your 0 to 360 degree output. Remember, if the magnet is not exactly centered above the sensor, you will get a sinusoidal error on the output, and the chip can calculate out that error using a whole lot of factors here. And we will have at one point a look at those, I promise. The EEPROM is used to load the SRAM at power up or hard reset with all the configuration data. So you find all the configuration data we saw in the SRAM also here in the EEPROM. So there is not a one-to-one mapping. So the bits here are all over the place, and yeah, the linearization stuff here is at slightly different addresses. Oh no, it's exactly at the same address. It also starts at 0C. Yeah, it's not one-to-one. And at the very end here, we also have some more bits that are used for other purposes and won't show up in the SRAM at all. We already saw in that graphic that you are using the primary registers to access the extended addresses. And for reading an extended address, you need these three registers here. The extended read address, which needs to contain the extended address you want to read, so 16 bits. Then the extended read control and status register, which is also 16-bit, like all primary registers. But in the first byte, we have here a execute read bit, which you have to set to initialize the read from an extended address. And in the second byte here, that is actually the least significant byte, you have at the very end, so bit 0, a read done bit, which is in turn set by the by the chip when the read of the extended address has been successfully finished. And then you find the 32-bit data from that extended address, or generated by the command initiated by the extended address, here in the extended read data register, which is actually two 16-bit registers, so 32-bit in total. Now, what I've just told you is written down in the programming reference on page 33. On page 34, you find that nice graphic here, which continues down below, detailing the whole process. We first do a write transaction on the I2C bus to the A1335. Starting, of course, with the slave address, last bit being 0, so it's a write transaction, followed by the address of our primary extended read address register, which we fill with the 16-bit extended address, most significant byte first, and the transaction ends with just writing the most significant byte, so the first 8 bits of our extended read control and status register, with the first bit, the extended read execute bit set to 1. And that ends our first transaction, and you can do that simply by an Arduino wire transmission. Then we do a retransaction. So we transmit the slave address again, but this time the last bit set to 1, so it's a read. And the A1335 will reply first with the second byte, the least significant byte, from the extended read and control register, with the last bit here, our extended read done bit, hopefully set to 1. That is followed by the 4 bytes of our extended read data register. So 32 bytes in total for the extended address we just read. And we can do all that in an Arduino wire request. Please note that this only works because the last byte we wrote to the A1335 was the first byte of the extended read control and status register, and that automatically advanced the internal I2C register pointer of the A1335 to the second byte inside the extended read control and status register. So our read starts just there. Also note that we don't release the bus between the two transactions. So we don't send a stop signal on the I2C bus, just a restart. And if we implemented the whole shebang here just like that, it simply wouldn't work. Believe me, I've gone through it. I've gone through a lot of pain regarding this, because on the next page, page 35, there is another chapter, Extended Access Command Set, with a lot of text. And I'm sorry, we have to read through that because I initially didn't. I always preach, read your datasheet, but I thought after seeing that detailed diagram, I'm really done in regards to reading extended addresses. Turns out I wasn't. So here's the important part. The extended access operation is then initiated by setting the appropriate extended read control and status register execute read bit and polling for the extended read control and status register extended read done bit. The latter polling is generally necessary because the processor only accepts a new extended command when it is not actively processing angle readings. Extended command here refers also to reading the SRAM or the EEPROM. There can be a delay from the time the command is initiated to the time the processor begins acting on the command. The longest time for a command to be recognized by a processor is less than 128 microseconds. Execution time of the command varies from 2 to 3 microseconds for SRAM reads and writes to almost 40 milliseconds for some of the self-test diagnostics, the commands. Unless otherwise stated for particular access, the command execution time is less than 4 microseconds. Waiting for completion longer than the worst case time is possible, but for maximum flexibility, polling for the done bit is recommended. So, in effect, if you do your transmission here and then immediately your request, you never get the data you want. And here we have the private function of the library implementing the whole shebang. Read extended address. It gets as an argument the 16-bit extended address which we want to read, and it returns here the 32-bit of extended data which we hopefully will have read. Should anything go wrong, it returns false, like all these functions of the library that can fail, and you can use last library error to retrieve the exact error. Inside the function we first have a block of 4 constants here, and please note I'm using this time constant expression. Thank you to Mike Lopez for pointing that out to me. This will actually enable the compiler to handle these things here like, how could I put it, it's a define. So really not create code that is executed at runtime to set these values where they are used, but to really statically include these values in the code where they are utilized. I also included this time the constants in the function itself because they won't be used anywhere else, and yeah, so I keep it nice and tidy inside the function. Anyways, we start of course with the primary register extended read address, which we will write to, and then I have here these primary register extended read control and status most significant byte execute flag. So yeah, the very first bit, and the same here for the least significant byte, the read done flag, the last bit here in the least significant byte. And I also have here, just for better readability, data size for the data I will read from the chip, which is 1 byte, yeah, the least significant byte of the extended read control and status register, plus the 4 bytes of the actual extended read data register. Then we have 2 variables here, 8-bit status, just to store the 2-wire and transmission status that might be returned, and the data array with those 5 bytes which we will actually read from the chip. And then we start the action. And we do that by exactly following that diagram, which we know by now, reading the very last chapter there is not exactly working, but anyway, we start with it. So we do a begin transmission here to our I2C address, so our A1335. Then we write the primary register extended read address, which we want to write to, and then we write the next 2 bytes, the extended address here. Note again, most significant byte first, and finally we write the most significant byte of the extended read control and status register here with the execute flag set. And then all that's left to do is end transmission. Please note that this gets as an argument false, because I mentioned that we don't release the bus after writing that data. We keep the bus, we just do a restart. And should that fail, of course, I set my last library error with the error that occurred, and I return false, and we failed in our mission. Step 2, actually reading the 5 bytes we require from the chip. And before we even go into step 2, I have here a delay of 1 millisecond. Remember, the datasheet states that it might take up to 128 microseconds for the CPU even to consider our request. And then for most read operations, another 4 microseconds until they are finished. I tried here delay microseconds with about 200 microseconds, and it simply didn't work. So I ended up putting in here, not fiddling with that, just a delay of 1 millisecond. I mean, polling is recommended in the datasheet, so we will revisit that part anyway at some point. Okay, then we do a request from our device, so I2C address of our A1335 with the data size, the number of bytes we want, 5 in that case. And this time the function also gets as an argument true. That is, after that we will send a stop signal and release the bus. Should we not exactly receive 5 bytes, then we throw another last library error here and exit the function with false. Next step, and this is really just me being paranoid, we check if really 5 bytes of data, so our data size, is available in the 2-wire buffer. And if that's not the case, we throw an error. Then we read those 5 bytes from the 2-wire buffer in our own data array. And if we don't get 5 bytes, we throw an error again. Finally, we check if the extended read control and status register contains in its least significant byte actually the ready flag. That should be stored, the least significant byte here, in our first element in our data array. And if that's not the case, we throw another library error. That's a new one, library error extended read done flag. And if that is also okay, we take the next 4 bytes, bring them into the right order, and write them into our extended data variable. And then we're done. You remember that read ROM version, so 4F extended address, which might prove useful to verify if our read extended address stuff is really working. I implemented 2 high-level functions, public functions in the library for that. The first one, read ROM version, uses read extended address to read exactly that extended address. I have a private constant here for that, and it stores the result in a private member variable extended command ROM version data. And the second function here, ROM version, does nothing else but returning that private member variable. I have also here 2 new public functions, read output rate and output rate, but we will talk about those in detail in the next installment. I just mentioned that because I'm actually using them in the Arduino sketch. In the header file, in the public part of the class, I define, of course, my read output rate, read ROM version, and ROM version functions. In the private section, I have here my 32-bit extended command addresses, the constants, that is, for the extended command output data rate address and the extended command ROM version address. Please note, throughout here in the header file, I'm now using also constant expression instead of expression. And finally, also in the private section of the class, we have here the buffer variables for extended command output data rate and the extended command ROM version data. Within the sketch itself, inside the setup function, I use all these new methods we created to read the ROM versions of my left and right chip. If something should go wrong, I print out the library errors that occurred, and I also read the output data rate of the left and right chip. Again, more details about that in the next installment. Afterwards, I print all the values I just read out on the serial port, and I also, just as a marker, print out finished setup. And that's how the whole thing looks at the serial monitor. Pretty unspectacular. Okay, so here we have the data, which is regularly polled with angle, the temperature, and the magnetic field strength. We saw that in the last video. But here is a new part where I print out the left and right ROM version, and it is indeed 133500BA. like promised in the datasheet. So our read extended address stuff is actually working. And again, we will talk about the output data rate in the next installment a little bit more in detail. That's it for today. Admittedly, another very short video and only a very small step for the microcontroller community wanting to use an A1335. But I'm still quite pressed for time, so I only have an hour here and an hour there to do actually YouTube stuff and program my little Arduino here. Anyways, you find the code as always on my Google Drive, link in the description. Next time we will revisit that read extended address method and implement a proper polling of that read done flag. And we will also implement a write extended address method, which will hopefully be a little bit easier going. And we will finally have a detailed look at that read output rate stuff, which will lead to some experiments, hopefully, in regards to noise. We'll see. Till then, bye.